Hello, this is our Chapter 7 video for Introductory Chemistry. It is called Chemical Reactions. So we're going to look at what drives a reaction to happen and how to predict what the products will be, and then a few different ways on writing those reactions. This chapter has no math in it. So usually that means some people are happy about it, and some people aren't. It just kind of depends on what your skill set is. So we're going to start with kind of introductory information, definitions. Oh, sorry, that was a bad sound. Here we go. Just adjusting my setup here. And this reaction at the bottom is showing octane reacting with oxygen in an engine to produce carbon dioxide and water. So what we want to gain from this picture is that the reactants are always going to be on the left-hand side, and then we have the arrow in the middle, and the arrow is telling us that something new is forming. So we can say that the products yield, or excuse me, the reactants yield products, the reactants react to form products. But on the right-hand side are always our products. One other thing over here, it says elements are not transmuted during a reaction. So that means they don't change into something else. We can't turn carbon into sulfur. We can't turn lead into gold. It is not magic. Now, we know the difference between a physical change and a chemical change, but we also talked about that it's a little bit difficult to tell the difference if we're just looking at something. And the same is true for a chemical reaction. Technically, a chemical reaction happens at the molecular level, but because we can't see that, we have to have some clues to help us know if a chemical reaction has occurred. So we have a color change, and this could literally be a color change from blue to red, but it could also be the fading of a color. A precipitate formation. So a precipitate is another word for a solid. So this is a solid that's forming. And our example is right here. So all of that white down there is a precipitate. A precipitate, a solid in a chemical reaction, is anything we can't see through. So it can even be cloudy and just kind of throughout a liquid, dispersed throughout a liquid. And that counts as being a solid. Gas bubbles. So you can see down here we have a reaction with some gas bubbles. A large energy change. So either something that becomes very hot or very cold. So when I think very hot and very cold in terms of chemical reactions in the real world, I always think of those instant heat and cold packs. I don't know if you have any of these, like in a first aid kit. We keep them around in case of injuries, but you just kind of pop a bubble inside of them and it allows a chemical reaction to happen. The other one on here is emission of light. So we do have a burning of gas, and we have a glow stick over there. And then other clues could be a new smell, a whooshing sound from a tube. So that would be an indication that a gas has formed and that it is escaping very quickly, or a permanent new state. So if we only had liquids and now we have a solid that's staying there, this would be an example that a chemical reaction has occurred. So let's look at a chemical equation. And we're going to talk about all of the parts of it. It is a shorthand way to describe a reaction that's occurring. We know that the right-hand side are the reactants. I think I said the right-hand side, didn't I? I'm sorry. The left-hand side are the reactants. The right-hand side are the products. So that's that piece of information. The next one says the states of reactants and products. So after each chemical, there's a letter in parentheses, and this is telling you the state. Our options are S for solid, L for liquid, G for gas, and AQ. AQ stands for aqueous. And it's very difficult to mix a solid with a solid. So oftentimes we dissolve it in a solvent. And our most common solvent is water. And so the word aqueous means that we have our solid dissolved in water. The next one says the relative number of reactants and products. So we have some numbers in front of our molecules. These are called coefficients, and these are what we put in there to balance our chemical equation. And we're going to talk about balancing chemical equations for the next couple slides. And one of the reasons we have those numbers is that last check mark down there. It says that we can use these to determine weights of reactants used and products that can be made. So the math that we did in chapter 6, we're going to do very similar math with our chemical reactions in chapter 8. Another reason we balance chemical reactions is because of the conservation of mass. Matter cannot be created or destroyed. So if we start with 4 carbon atoms on the left, we have to end with 4 carbon atoms on the right. So we're going to talk about how to balance a chemical reaction. And this is something that people will struggle with, but I'm going to show you a couple little tricks on how I do it. And I actually have 3 examples on this slide, and these are all examples that require maybe a little bit extra effort. So these aren't the easiest of examples because I wanted to show you how to approach a problem that isn't as straightforward. But here's how I do it. I start by writing down every atom, every type of atom in the reaction. So our first reaction is NH3 plus O2 makes NO and H2O. So we have nitrogen, hydrogen, and oxygen. And I like to put it right at the arrow because then on the left side of each of those atoms, I'm going to put how many of each of those atoms are over there. So there's 1 nitrogen, there's 3 hydrogens, and there's 2 oxygens. So I'm just using the subscripts from those chemical formulas to figure that out. On the right-hand side, 1 nitrogen, 2 hydrogens, and I have 2 oxygens, 1 from each of those molecules. Now, with my little cheat sheet here, I can see that my nitrogens are balanced. I have 1 on each side, and my oxygens are balanced. I have 1 on each side. But my hydrogens aren't. I have 3 on one side and 2 on the other. So in order to get them to balance, I need to have the same number of each of those atoms on each side. So right now we have 2 and 3. So we want to think of the least common multiple, and 3 and 2 is going to be a common one for us. The least common multiple between 2 and 3 is 6. So that means that I'm going to put a 3 right here, and I'm going to put a 2. I didn't leave myself enough space there, but I'm going to put a 2 right there so that I can have 6. So now I need to adjust my little sheet. So I now have my 6 hydrogens, but I also changed the number of oxygens over here. So I have 3, 4. Now on the left-hand side, I have those 6 hydrogens, but I also changed my number of nitrogens. So now the hydrogens are good, but nothing else is. So the next thing I'm going to balance are the nitrogens. And the reason why I'm doing the nitrogen first instead of the oxygen is because the oxygen is all by itself on the left-hand side. So I can put any number I need to right there, and it will help me balance that chemical equation. As opposed to when I put a number right here, it doesn't just change the nitrogen, it changes the oxygen as well. So when you have an element that's by itself, leave it till the end. All right, so to balance my nitrogens, get rid of that line, and I'm going to put a 2 right there because now I have 2 nitrogens. But I also changed my oxygens when I added in that number. So I need to adjust my oxygen number again. I have 3 from the water and 2 from the NO, so I have 5 oxygens. Nitrogens are balanced. Hydrogens are balanced. Oxygens are not. My right-hand side has 5. My left-hand side only has 2. So what we want to think is, what number can we put right here that would allow us to balance out the oxygens? And what I'm going to put right there, let me erase my lines, is a 2.5. Because 2.5 times the 2 atoms will give us a 5. Now that's not our ending point. We can't have half of a molecule, but the ratio is correct. So right now we have a 2 to 2.5 to 2 to 3 ratio. What we want to do is multiply all of those by 2. We want to double all of them because that will get rid of that fraction. So my final answer is I'm going to have 2 ammonias. Let's see, move where I write this. I'm going to put it at the top here. 2 ammonias, 5 oxygens, 4 NOs, and 6 waters. The numbers that are in my little tally sheet are going to be still balanced, but they're just going to be twice as big. So that's a good way to balance out a chemical reaction when you have an element that's all by itself and when you need to use a fraction to help you out. Okay, let's look at this next one. We have aluminum sulfate reacting with calcium hydroxide to make aluminum hydroxide and calcium sulfate. So I'm going to write down what I have. Aluminum, SO4. I am going to leave this as sulfate. And the reason why I'm able to do that is because on both sides of the equation, it's in the form of sulfate. And so I don't need to worry about counting the sulfur separately from those 4 oxygens because it stays in the same format. And then I have calcium and hydroxide. And same thing with the hydroxide. We have the hydroxide paired up with the aluminum and paired up with the hydroxide, and it stays as a hydroxide. All right, so here comes our count. On the left-hand side, we have 2 aluminums, 3 sulfates, 1 calcium, 2 hydroxides. On the right-hand side, we have 1 aluminum, 3 hydroxides, 1 calcium, and 1 sulfate. So right now it looks like the only thing that's balanced are the calciums. Nothing is by itself, so this doesn't really give me a good indication of where to start. The hydroxides, we have a 2 and a 3, so similar to the math we had to do for the last one. So I'm going to start there because I know that if I start somewhere else, I will probably have to do my numbers more than once. So that 2 and 3, I'm going to put my 3 right here because now I have 6 hydroxides, and I'm going to put a 2 right there, and again I have those 6 hydroxides. So I'm looking for that least common multiple. I do need to adjust my other atoms. So on that left hand side, I now have 3 calciums, and on the right hand side I now have 2 aluminums. So my hydroxides are balanced, my aluminums are balanced, but now I need to look at my calciums and my sulfates. But look at what we have. On the left-hand side, we have 3 of each of those. So all I need to do is put a 3 right there. And now my calciums and my sulfates are balanced. So the purpose of this example was to show you that when we have polyatomics that are in the same format on the reactant and the product side, we can leave them in their polyatomic form when we're counting them. All right, last example here. We have phosphoric acid reacting with potassium hydroxide to make water and potassium phosphate. This is an acid-base reaction, and I know that because we're starting with an acid and we're reacting it with a base. Hydroxide is a type of base. And this is a reaction type that we'll talk about later on in this chapter. But why that matters here is because instead of water, I'm going to write this as HOH. So I'm going to write it like it's a cation and anion, because that's going to help me with counting my atoms for balancing. So let me write down what we have. Hydrogen, phosphate, potassium, hydroxide. Now when I look on the left-hand side, there's my hydrogen, there's my hydroxide, potassium, phosphate. So it matches up with our ions on the left-hand side a little bit better. So I have 3 hydrogens, 1 phosphate, 1 potassium, 1 hydroxide. On the right-hand side, 1 hydrogen, 1 hydroxide, 3 potassiums, and 1 phosphate. So as of right now, the phosphates are balanced and the hydroxides are balanced. So let's start with the potassiums. I'm going to put a 3 right here. So that means my potassiums are now balanced, but that also changed my hydroxides to 3. So now my waters are no longer balanced. So I'm going to put a 3 right here, but now I have my... Oh, I'm sorry. Oh yeah, that is correct. I was looking at the wrong one. So here's the reason we write it as a hydrogen and a hydroxide instead. Because if I think of it like this, I have 3 hydrogens and I have 3 hydroxides. And now our equation is balanced. So if you break the water apart into a hydrogen and a hydroxide, it helps your counting a little bit better. It just makes it a little bit easier. So we do need to define some words. And the words we need to define are aqueous, which we talked about. We said that when chemicals dissolve in water, this is called an aqueous solution. And then the other 2 words on this slide are soluble and insoluble. Soluble is the description we use for a chemical when it dissolves in a liquid. So if something dissolves in a liquid, we say that it is soluble. If something does not dissolve in a liquid, then it is insoluble. So we're going to use these words a lot, so it's important to understand soluble means it will create a solution, it dissolves. Insoluble means that it does not. And another way to phrase this or kind of add on to this, it means that it will stay a solid. Now when things are soluble, they will dissociate. So we have an example up here of NaCl. When NaCl, when table salt is put into water, there aren't any sodium chloride units left behind. They all break apart or dissociate into sodium cations and chloride anions. If we have a polyatomic, so the example that's down here is silver nitrate, the ions break apart, meaning we get silver cations and nitrate anions, but the nitrate, that polyatomic, does stay together in its grouping. When something does break apart, when it forms those ions, it's called an electrolyte. So I have Gatorade up there because one of the things we always know about Gatorade is that it contains electrolytes, which really just means it has ions in it. And so there's a lot of ions that our body needs, sodium, potassium, for example. But when Gatorade says it contains electrolytes, it's really just saying it contains ions. There's different types. If we use just pure water and try and power a battery to turn on a light bulb, nothing happens because pure water by itself is a non-electrolyte. There aren't any ions in it. But if we do the same thing and add some salt into that water, the light bulb lights up, because our sodium chloride water solution is an electrolyte solution. Now, when things are electrolytes, when they light that light bulb up, we can go a little bit further with the definition. And we can break it down into these three categories: strong electrolyte, non-electrolyte, and weak electrolyte. A strong electrolyte, and that's this one over here, sodium chloride, all of the molecules break into their ions, and it conducts electricity very well. So this is something that we would consider to be soluble. Non-electrolytes, we aren't going to get any ions. So none of the molecules break apart, and we won't get any electricity from it. This is going to be one of our molecular compounds. It doesn't break apart into ions because it doesn't have any. If it's made from just nonmetals, there aren't any ions in it. And then the last category is kind of our gray area. Oh, this is our molecular compound down there, that's sugar. The last category are weak electrolytes. And with a weak electrolyte, we will get some ions. A small percentage will break apart into ions. So that means the light bulb will turn on, it just won't be as bright. An example of this is hydrofluoric acid. It breaks apart into hydrogen ions and fluoride ions. But I'm going to erase that arrow right there, because what really happens is that it will break apart, but those ions that broke apart can recombine and go back into that molecule form. And so only a small percentage of them are actually in their ion form at any given time. We're definitely going to be focusing on the soluble compounds for this as we talk about our reactions. So again, here's those couple of words. Soluble is when a compound dissolves in its liquid, and insoluble is when it doesn't. But the question is, how do we know? If we're doing this on paper and we want to be able to predict, will a chemical dissolve or not? Will it be soluble? The best way is actually just to figure it out, meaning put it in water and see what happens. But this has been done for us, many years worth of data, and we have tables that will explain the results for us. So this is straight from your book. This is called a solubility table or solubility rules, and there's really 4 sections to it. The section that's on the left-hand side are our ions, and on the top half it says compounds containing the following ions are mostly soluble. And the bottom half says compounds containing the following ions are mostly insoluble. Now, if you're trying to figure out if something's going to be soluble or insoluble, you don't need to find your cation and your anion. You only need to find one. When you find your ion, though, you do need to look at the right-hand side of the table. The right-hand side of the table are the exceptions. So, for example, up here, these guys are soluble except when one of these cations are paired up with it. And same thing down here. These are insoluble except when one of these anions, or excuse me, one of these cations is paired up with it. So we're going to practice this. We're going to determine if each of the following compounds is soluble or insoluble in water. Now, in order to do that, we do need to look at our table. So here's our table. So the first example is KOH. So the first thing I see is potassium. And potassium is in the section that says these ions are soluble. We check the exceptions, and for potassium, there are no exceptions. So I know that potassium hydroxide is going to be soluble. The next one is silver bromide. So I see my bromide right here. So it's in the section that is soluble. I check the exceptions. When any of these ions is paired with silver, mercury, or lead, the compound is insoluble. So even though bromine is soluble most of the time, when it gets paired up with silver, it is now insoluble. The next one is magnesium hydroxide. So here's my hydroxide. Hydroxide is in the insoluble category. And I read my exceptions over here. When either of these ions pairs with lithium, sodium, potassium, or ammonium, the compound is soluble. When hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble. So no mention of magnesium. So that tells me that it is insoluble. And then last but not least, looking for a color I haven't used. How about orange? Strontium sulfide. So there's my sulfide. And again, we're going to check those exceptions. So sulfide's in the insoluble section. When either of these ions is paired with lithium, sodium, potassium, or ammonium, it's insoluble, or it's soluble. When sulfide is paired with calcium, strontium, or barium, the compound is soluble. All right, I'm gonna pause and go shut my window so you guys don't have to listen to my neighbor's dogs barking. Okay, hopefully that will help. I'm sorry about that. So we're going to move into the section of the chapter where we're looking at reaction types and predicting products, and even just predicting whether a reaction will occur or not. And our focus is going to be aqueous reactions or water-based reactions. And in order for a reaction to occur, it has to have a driving force, meaning there has to be a reason for it to occur. And the four that we're looking at here are the formation of a solid, the formation of water, the formation of a gas, or the transfer of electrons. So each of these is a different reaction type that we're going to cover. And the first one is the formation of a solid. And this is called a precipitation reaction because we said that a solid is called a precipitate. And I'm going to write at the top here kind of a generic form of this equation. In order to have a precipitate reaction, we're going to react an aqueous compound with an aqueous compound, and it's going to give us a solid and one more aqueous compound. So it's good to know this, and this will make a little bit more sense later, but as we are filling in products, this will be one of the ways we can figure out what reaction type we're looking at. So here's an example. We have lead nitrate reacting with potassium iodide. So notice we're starting with two aqueous compounds. When they react, they're going to form potassium nitrate and lead iodide. So an aqueous and a solid. One thing I do want to point out, notice that their solid is written second, and when I did my example it was written first. It doesn't matter. It doesn't matter what order the chemicals are written in on either side of the equation. It just matters that the reactants are on the left and the products are on the right. So in our picture here, we can see our potassium iodide adding to this clear colorless liquid, this lead nitrate. And when they react together, we get this yellow solid. We get this lead iodide solid, and then the potassium nitrate is just forming as a result. One more thing I want to point out here is notice the cations and who they're paired up with. What we're going to do as we write out these products is we switch the cations. So the lead gets paired up with the iodine, the potassium gets paired up with the nitrate to make our two products. So here's the same reaction in kind of cartoon form so we can see what the atoms and the molecules are doing. So here's our potassium iodide before they've been mixed together. So we have potassium and iodine ions. Same thing with the lead nitrate. We have our lead cations and our nitrate anions. Here they are when they first get mixed together, just a bunch of ions. And what happens is that our lead iodide is going to form a solid, and then our potassium and our nitrate will still be dissolved in that aqueous state, so in that solution form. Now, if we do this on paper or in person, and we react to chemicals, and the result is two aqueous compounds, what's really happening is no reaction, because we started with potassium and iodide and sodium and chloride in their own separate containers, but then when we mix them together, it's still just a bunch of ions floating around. They're just now in the same container, but nothing was strong enough. There weren't any attractions that were strong enough to create that solid. Now in person, this is easy to see because there's no solid forming. But on paper, how we know is we go back and look at that table. So we go and we look up KCl, we look up Ni on that solubility rule table to see if they would be soluble or insoluble. So we're going to practice that. We're going to write out a full equation. This is how we predict products and complete a reaction. The first step is that we break our reactants into ions. And then we're going to exchange ions. So we take the cation from one and the anion from the other. We make sure that the charges are balanced within our new compounds to get our new formula. So we're figuring out what those subscripts are. We balance the equation as a whole. And so for this, we're just adding coefficients. We can't change the subscripts here because the subscripts were used to balance out those charges. So we don't want to mess up the charge balance. And then last, we're going to fill in the state for each of our chemicals, solid, liquid, gas, or aqueous. And if we ended up with all aqueous and started with all aqueous, then there's no reaction. So here's our problem. We're going to write a complete balanced equation for the reaction between NABr and PbNO32. And I have our steps over here in that purple box, just kind of in a shorthand version. So the first thing we're going to do is we're going to write out the ions. So this does require us to know charges. So sodium and bromine, we know their charges because of where they are at on the periodic table. Nitrate we know because of our T43, we know we have those polyatomics memorized. And then lead is one that can be different charges. It's one of our transition metals. But if we know that nitrate is a 1-, and there are two of them, so that means that there are two minuses altogether, then lead has to be a 2+ to balance that out. So we have them broken up into their ions. Now we're going to swap their partners. Sodium goes with nitrate, lead goes with bromide. Remember that when you write these out, the cation has to go first. So I'm going to fill in my reactants. I'm going to leave some space here in case I need to put in coefficients for balancing though. So my first new product is Na with NO3, and I can see that they both have a 1 charge, a 1- and a 1+, so I can just combine them in that ratio, and I'll leave parentheses there to be filled in later. And then I have Pb2+ and Br with that 1-. So I'm going to take that 2 and write it as PbBr2. So my charges are balanced. The next step is to balance the entire chemical reaction. So I know that I have sodium, bromine, lead, nitrate, 1, 1, 1, 2, 1, 1, 2, 1. So I'm going to balance my bromines first. No real reason except for it was first on the list. So my bromines are balanced, but I also messed up my sodiums when I did that. So then if we balance out the nitrates, I need 2 nitrates. Look at that. It also balanced out the sodiums. Now if you're doing this and you can't balance your chemical equation, it's just not working out, it means that when you wrote out the formula for one of your products, the charges weren't properly balanced. If your charges aren't balanced, then your chemical equation won't ever work out. All right, I need to fill in those states. I need to know if NaNO3 is solid, liquid, gas, aqueous. Same thing with that lead bromide. So here's our table. We had our sodium nitrate. There's my nitrate and my sodium right next to each other, and notice that neither one of them even have exceptions. So sodium nitrate is soluble, and our abbreviation for that is going to be AQ because I know that it's aqueous. So soluble means that it dissolves in the liquid. Aqueous means that it specifically dissolves in water. And then we have lead bromide. So let me change colors on us. There's my bromine. It's in that soluble section, but when I look at the exceptions, there's the silver. So that tells me that silver bromide is going to be insoluble, and the way that we indicate that is with an S for solid. So there's my final answer, my balanced chemical equation. It has coefficients to balance the atoms, it has states, and it has products that have been balanced for charge. Now, the type of equation that we just did is called a molecular equation. All of the chemicals are written as their molecules. For example, this one. This isn't actually the most accurate though, because things that are aqueous actually break apart into ions in water. They are disassociating, they're electrolytes. And so in order to make it a little bit more accurate, we can write out what's called a complete ionic equation. Anything that is aqueous gets written as its ion form. So we have our original equation up here. We have KOH aqueous. It is now written as potassium positive, OH minus. Notice that that coefficient went to each of them. We have MgNO3 2 aqueous, so we have a magnesium 2 plus and those two nitrates. And notice that our subscript for that nitrate became the coefficient. And then our potassium nitrate gets broken out into potassium and nitrate ions. And our magnesium hydroxide solid stays a molecule. The only thing we're going to break apart here are aqueous compounds. So the aqueous, we're going to write them as ions. Now this is a very full report of what's happening, but we have one more way to do it. When we look at this big long equation, there's some items on the left and the right hand side that exist on both sides. For example, potassium and nitrate. These are called spectator ions. And if we remove those spectator ions, we get our final type of equation, which is called the net ionic equation. And so this is showing how that solid is being formed without those spectator ions in it. So we're going to take this reaction that we just did a couple slides ago, and we're going to write out the net ionic equation and the complete ionic equation. So I'm going to start here at the beginning. 2 Na plus aqueous, 2 Br minus aqueous, lead 2 plus aqueous, 2 nitrates aqueous. Also, this takes a lot of space. 2 sodiums aqueous, 2 nitrates aqueous, and then that lead bromide, that's our solid, that's going to stay in our molecule form. So there's my complete. So my complete ionic is the one that's going to be in green. Now, excuse me, To get to my net ionic equation, I need to remove my spectators. So I'm going to circle my spectators in purple. So if we look at the left and the right hand side, we have sodium and we have nitrate. And so I'm going to write out my net ionic equation in red, and really I'm just writing down everything I didn't circle. Oh, I see a typo in my above equation there. I forgot the B in lead. There we go. All right, so there we go. We have our complete ionic. We identified the spectators so that we could write the net ionic. So we do have a couple reaction types left. The next one is called an acid-base reaction, and it's just what it sounds like. An acid and a base react to make salt and water. So here's our example. We know that this is an acid because it starts with a hydrogen. We know this is a base because it has hydroxide in it. And we're going to make calcium and nitrate. Now, if we think of water as HOH, just like we did when we balanced it, the same type of reaction is occurring. And what I mean by that is calcium's getting paired up with nitrate, hydrogen's getting paired up with hydroxide. So we're following that same format. The net ionic equation for our acid-base reactions is going to be the hydrogen plus the hydroxide making water. When we break this apart, liquids don't break apart. So as long as this salt is soluble, then our net ionic equation will just be the formation of the water. So we're going to practice again. Here's our reaction. We're going to react nitric acid and calcium hydroxide. So there's my nitric acid. There's my calcium hydroxide. And I'm going to do molecular, complete ionic, and net ionic. So we're going to do all three. So in order to start, our first step was to break it apart into our ions. So I have hydrogens, I have nitrates, I have calciums, and I have hydroxides. Now notice that I don't care that I have 2 hydroxides up there. I'll take care of that when I'm balancing the chemical equation, but as of right now, it doesn't matter how many we have. We just want to know what we have and what their charges are. So my calcium is going to get paired up with my nitrate. My hydrogen is going to get paired up with my hydroxide. And for right now, I'm going to write it as that. Anytime water forms, it's going to be a liquid. It won't ever be aqueous. Water is not going to dissolve in water. If it's a hot reaction, it might be a gas because we might form water vapor instead of just water. And then when I pair up my calcium and my nitrate, we have that 2 there. That's going to become my subscript. So I'm going to have CaNO3, 2. I'm going to leave a little parentheses there to fill in my state. Oh, I thought I had a cheat sheet on my next slide. For that calcium nitrate state, you might remember that nitrate is one of our ions that is always soluble and has no exceptions. So I'm going to fill in aqueous here because I know already that it will be aqueous. So we've split it into ions, we swapped their partners, we balanced the charges, we figured out the states, and so now I'm going to balance the chemical equation. There's my ions. I have 1, 1, 1, 2, 1, 1, 1, 2. So I'm going to balance out the nitrates first. I'm going to put a 2 right there. So now I have my 2, I have my 2 nitrates, but that also changed my hydrogens. So I'm going to put a 2 right there. So now I have my 2 hydrogens and my 2 hydroxides. So there we go. This is my molecular equation. Now, because we have all of that work completed, writing out the complete ionic equation is fairly simple because we have a lot of the information underneath it already. Well, time-consuming and busy and annoying. Sorry, I keep leaning my arm on my mouse pad. But simple. So 2 hydrogens, aqueous, 2 nitrates, aqueous, calcium, 2 hydroxides, now that water, it's going to stay together. And 2 calciums and 2 nitrates. So there's my complete ionic. And then the last step is our net ionic. So I'm going to identify my spectators. It looks like we have nitrate and calcium as our spectators. So this is essentially what we predicted on the last slide. So if I rewrite that without my spectators, I have 2 hydrogens, 2 hydroxides to make 2 waters. And really, because these all have the same coefficients, we could just reduce that down so that it's hydroxide and hydrogen on my reactant side and water on my product side. So my net ionic equation, I'm going to circle in purple down here. All right, there we go. Our last type of reaction that falls into this same category is gas evolving reactions. And there's really 2 ways that a gas can form. The first one is the direct formation. So we have Ks and H2SO4. When the hydrogen combines with that sulfur, it makes H2S gas. The other is through an indirect way. So in this reaction, our hydrogen is going to combine with that sulfite. So it forms H2SO3, but H2SO3 isn't stable and it breaks apart into water and SO2 gas. So really, we should write this as H2O and SO2 gas. But in order to see that these are forming, we have to get to that H2SO3 first so that we can then replace it. Here's the 4 things you need to look for. So the H2S is the only one that forms directly. And then the other 3, all of these will form the gases that are shown and water. So the 4 molecules that are circled there, after we take our reactants and we swap them, these are the 4 things we're going to look for. So we know that it's a precipitation reaction if it forms a solid. We know that it's a acid-base reaction if it forms water. Also, we'll start with an acid and a base. And we know it's a gas evolution reaction if it forms one of these. So here's our practice. We're going to write a complete, balanced, molecular, complete ionic, and net ionic equation for the reaction between Na2SO3 and HNO3. So HNO3, Na2SO3. So I break them apart. I swap their partners. So Na goes with NO3. It's a 1 and 1 for their charge, so they're already balanced. And H goes with HSO3, or goes with SO3, excuse me. And I have that 2 there, so it becomes H2SO3. But this should give us a little red flag. We should see that and think, there's my little red flag. We should see that and think that breaks apart. So I'm not going to write that as H2SO3. I'm going to write it as H2O and SO2 gas. So I have my products written out. I need to do two more things. I need to balance the equation and I need to fill in the states. And really, there's only one more state to fill in. We know this is aqueous because sodium and nitrate are both always aqueous. So the last thing to do is to balance it out. So we have H, NO3, Na, and SO3. On the left-hand side, 1, 1, 2, 1. On the right-hand side, 1 sodium, 1 nitrate. Now the water, we have to leave it as H2O. We can't think of it as an H and a hydroxide because there aren't any hydroxides on the reactant side. So I have 2 hydrogens. Oh, you know what? I can't write it as SO3 either because on the right-hand side, it's SO2. So I need to break apart my sulfurs and my oxygens. So 1 sulfur, 3 oxygens. 1 sulfur, and then I do have 3 oxygens over there because I have the 2 from the O2 and then the 1 from the water. So it looks like what's not balanced are the sodiums. So I'm going to put a 2 right here. So now I have 2 sodiums. Got to adjust my nitrate. And then if I put a 2 there, that fixes my nitrate and my hydrogens. So there we go. That is my complete molecular equation. And now if we do this one in our net ionic, I'm going to erase my balancing just because it's going to be a little bit busy down here already. There we go. I'm going to have 2 hydrogens. I'm going to put my states underneath because it's going to take up a lot of space. Aqueous, 2 sodiums, aqueous, sulfite, aqueous, 2 sodiums, aqueous, 2 nitrates, aqueous. We only break apart aqueous, so my next 2 compounds are going to stay as molecules. Water and SO2 gas. So there's my complete ionic in green. All right, last is our net ionic. So we're going to look for our spectators. Nitrate, sodium. So I'm going to rewrite my equation without those. 2 hydrogens, sulfate, water, and the SO2 gas. So this one's a little bit different because it has the liquid and the gas in it, but the idea is the same. We're only breaking apart the aqueous compounds. There's one more type of pattern that we need to be able to identify in a reaction, and this is called an oxidation-reduction reaction. It's often abbreviated as just redox. And these ones fall into their own category because they don't have that same switching pattern that we just saw. In an oxidation-reduction reaction, there's one element that's being oxidized, which means that it's going to lose electrons, and one element that's being reduced, and that means it's going to gain electrons. And we can't have one without the other, because if an element's losing electrons, they don't just go out into space, something else has to gain them. One way to remember this is oil rig. So oxidation is the loss of electrons. Reduction is the gain of electrons. Just one of those silly phrases that might help you. Here are some types of oxidation-reduction reactions. We have 3 types on here. The first one says a substance reacts with elemental oxygen. So this is also called a combustion reaction. And when a combustion reaction happens with a hydrocarbon, meaning hydrogens and carbons, we will always make CO2 and water. The second type is a metal reacting with a nonmetal. So they both go from being neutral to being charged. And then the last one is if one substance transfers electrons to another. And this can be hard to see, but the way to recognize it is if we have a metal that's in a compound, but now it's free, that's one way to identify that this has occurred. So the big part of this chapter was classifying reactions based off of what happens, whether we make a solid, whether we make bubbles. We're going to talk about one more way on how to divide up our reaction types, and this is based off of what the atoms are doing, how the atoms are moving around. So we have 4 more categories: synthesis, decomposition, displacement, and double displacement. And we have some very generic equations there, but I'm going to give you a couple more specific examples. So first is synthesis. They have more than one name, of course, so they're also called composition or combination reactions. Here's how we identify them. We're going to start with 2 or more reactants and make one product. So if you look at all those examples down there, they each have 2 reactants, but only one type of product. So I like the name combination the best, but it's probably used the least because I feel like it's telling us what's happening. Decomposition is going to be the opposite. This is when we start with one reactant, and we're going to make 2 or more products. So each of these have one type of reactant, and they're making 2 or more products. Now the one that's a little bit different is that last example, but we are making more products than we started with. Next are displacement reactions, and more specifically, these are called single displacement reactions. So this is when we have an atom by itself, and it's reacting with a molecule, and now a new atom is by itself. So essentially it's switching places. So for example, our zinc switches places with hydrogen, our aluminum is switching places with the iron, and our sodium is switching places with the hydrogen. So in all 3 of these reactions, one element is displacing another element. So that's the single displacement. And then the last type is actually the one we've been doing the majority of this lecture so far. And let me move my face out of there. So these are called double displacement reactions. I like to call them square dancing reactions because they're switching partners. So this is when we have 2 ionic compounds that are exchanging ions. And so this is what we did with precipitation and acid-base and gas evolution. We took those reactants, broke them into their ions, and then swapped their partners. That is a double displacement reaction. And that is it for this chapter. Thank you very much.